behave like a set of waves, just like water wave, sound wave, and any wave could be represented by three variables. Is lambda, which is wavelength, and then is frequency, mu, and also is amplitude, which is related to the intensity of the light. Now those guys are related, those three variables are related. So C, meaning the speed of the light, gonna equal to lambda times mu. Okay, so they're related in that way. So let's do a few examples to define what we learned about wavelength, frequency, speed of the light, and etc. So if we have X-ray, which given you its wavelength to be 1.00 Armstrong. So what's 1 Armstrong equal to? So it's a length unit, and we usually use that for wavelength lambda. So let me just put it out 1. And A with a little circle on top is called Armstrong, which has a value of 10 to the minus 10 meter. Okay, this is very, very tiny, right? 1 meter, but that's 10 to the minus 10 meter. So that's the wavelength. And these dental hygienists take a series of dental radiographs while the patient is listening to FM radio station. Now you're giving what? You're giving mu. That is your frequency. So you get this is the frequency.
I can see how here there's not bad. I can still hear them.
See, this guy is the lambda, which is the wavelength. What is the frequency or wavelength of the electromagnetic radiation from each of the source? So for X-ray, we are given what? Given the lambda, which is the wavelength. Okay? We're given, so how do we find what we're trying to look for is what's the mu value, meaning frequency. We know they're related, right? Lambda times mu equal to what would that equal to? They're inversely related, longer the wavelength, shorter the lower the frequency. Equal to C, what is C? Speed of light, for light. Okay, those are for the electromagnetic radiation. We're dealing with the electromagnetic radiation because X-ray, if we index electromagnetic radiation range, and radio station, radio wave is also within that spectrum. So we're just using this equation, find the missing one. So C, let's just say we use so in this case for X-ray, we know wavelength, so we want to find the frequency, so therefore C over length, right? C, we could use the easy one, which is 3.00 times 10 to the 10 to the 10 meters per second, divided by its wavelength, which is 1 Armstrong, and it's amount to 1 times 10 to the minus 10 meter. Okay? So I always want you to start doing the cancellation of units. So cancellation of unit, meter and meter cancel out. You end up with what? You end up with what kind of unit? Second, per second. It's understood as cycles per second. We don't say cycles per second, we just say second. 1/2, okay? Second minus 1, okay? So that value turned out to be 3.00 times 10 to the 18 cycle minus 1 million per second. That many cycles per second, okay? We skip the cycles. And we also, cycles per second is also called hertz. Is that equal to 3.0 times 10 to the 18 hertz. That is Hz, okay? So you should be able to do the FM stations for that electromagnetic radiation is, let's see, for radio waves from FM radio station is 101. So let's see, also the lambda times mu. In this case, you know mu, right? So that's the frequency. So you want to find out lambda, or we just C over mu. C, like I said, is 3.0 using your 3 sig fig 1 times 10 to the 8 meters per second. Divide that by frequency is 101. So megahertz, mega is what? 10 to the 6. Okay. 10 to the 6. It has the megahertz. Hertz actually is what? 1/seconds. Okay. So going to be 1/seconds. So you can see second cancel out. We end up with 2.97 meters. That's the wavelength for radio wave. Is that good? Okay, let's look at number 2. Ask you which travel faster through a vacuum, electromagnetic radiation with frequency of this value, that many hertz, 10 to the 9 hertz, or cycles per second, or electromagnetic radiation with a frequency of 10 to the 30 hertz, or cycles per second. Which one travel faster? What? The 10 to the 9? Neither, but they're the same, right? Because they both are electromagnetic radiation. They travel at the speed of light. Okay, so just remember what we call electromagnetic radiation is just we use the term light to represent all the electromagnetic radiation, not just the visible light, like radio wave, microwave, all that. Okay, so they all have the speed. Electromagnetic radiation travel at the speed of light. So they all have the same, okay? So in this case, they travel at 3.0 times 10 to the 8 meters per second. So it's a kind of trick question. Okay, so what region does each of these radiation belong to? So what region out of the whole spectrum? So you guys gonna have to find out frequency equal to this value falls in what region. Okay, so I go back and look at, so refer to regions of the spectrum, the radiation spectrum, which is in your outline. Okay, it turned out that when the wavelength nu, when the frequency nu equal to 10 to the 9 hertz or cycles per second, that is still in the radio wave region. So it's radio wave. wave as the long frequency. Also, that is the long. So radio wave and small regions, also the same. Okay. Number 3. Can I move on, or is this what you said? Yes.
Is there any reason to not consider microwaves for 10 to the 9s? Because microwave has an overlap with.
Yeah, a little bit overlap, yeah. But when you have a bigger, if you have more precise electromagnetic radiant spectrum, it actually is more fall into the radio. It's your cell phone image. Okay? They do overlap with sometimes. Okay? It's just like, it's something that we give the name, right? It's not like the nature tells you that it's the radio. We just arbitrarily assign those different wavelengths, call it that name, just for easy reference, okay? Good question. Number 3, if a wave have a wavelength of this length and this frequency, what is the speed of this wave? What's the speed of this wave? Is that equal to 3.0 times 10 to the 8 meters per second? Is that right? All waves travel at the same speed? No, only the electromagnetic radiation, only light wave, okay? Electromagnetic radiation wave, all the region will travel at the same speed. But this one didn't say it's the electromagnetic radiation. So how you calculate out its speed next? What? Yeah, multiply, because speed is equal to lambda times mu, right? In this case, your lambda wavelength is 0.34 meters, and your mu is 0.75 hertz, or second minus 1 cycles per second. And when I multiply that out, is equal to 0.255 meters per second. Definitely a lot less than 10 to the 8 meters per second. Second part is the wave electromagnetic radiation? No, right? No, because the electromagnetic radiation, you would have traveled at 3.0 times 10 to the meters. Ask me speed of electromagnetic radiation equal to 3.0 times 10 to the 8 meters per second. So don't let that confuse you, okay? Light speed is different than water speed or sound speed. Sound speed. Travel, okay? Speed. Number 4, what is the energy of electromagnetic radiation have a wavelength of 10 to the 9? What type of radiation is this? Actually, I need to move on before, I don't think I introduced this yet. So let's go back to color. So we said electromagnetic radiation is a wave, and we could, using the lambda, nu, and speed, and amplitude to describe that type of wave. Now, in addition, if I say something is a wave, and we just had to look at 2 phenomena, is that set of wave. If something is a wave, then it could have these 2 properties. That means it will interfere with each other. Also, you will deflect. So those 2 things, those 2 phenomena, is unique to waves. Okay, so I said light is a set of wave because it possesses these 2 properties. interfere with each other, it can also diffract, okay? So what's that, what's interfering mean? Okay, so we understand what that means. So a set of waves interfere with each other to build each other up or cancel each other out. So as I show in here, when two waves, so it's wave number 1 and wave 2 coming in, if the two waves have equal amplitude, meaning that this part is the same, right? Same amplitude, the resulting wave, so when the two waves of the same kind comes in, at the same frequency and wavelength. Now, their amplitude could be different, could have different intensity. So amplitude related to intensity. Now, if they come in phase, meaning they come in step, meaning that the corresponding position lines up. For example, here I have a peak in this position. This is right at this position also. So they line up. So that means that they are going in phase, okay? So then what happened? The resulting one will end up with twice the amplitude, okay? So if I shine right light and the same right light in phase, then the red light and red light in phase, then the red light will be twice as intense, okay? So if they come in phase, so you can see this is twice as much as the original. So therefore, interfering, if you see something will interfere with each other coming as a set of wave, that means it will do that, it will interfere. And so that kind of push each other away, but interfere with each other. When you see the interference, then you could say that is a wave function, a wave property. Now, what if they come out of phase, meaning they completely out of step? So you have the peak aligned with the valley. So if those two have the same amplitude, same intensity, that means what? They completely cancel each other out. So this peak is going to cancel the valley, end up with what? Cancel each other out completely in this case. So this first one, we call that as what? Constructive interference, and this one cancel each other out, we call that as destructive interference. So that's something unique to wave only. Okay. On the other, the second property it exhibit is something called diffraction. So when you have a wave coming in, you come into an obstacle, but that obstacle has a little hole, a little slit, and that slit is incomparable to the wavelength. Then what happens? It will diffract, meaning it will just spread out. It will still pass through. That's that way. The set always still pass through, but it spread out. Does that make sense? So the wave still keep going when you have that slit. On the other hand, particles do not diffract. Okay, say I have bullets, particles coming through, they don't keep the same set of particles. Only the ones that fit into the slit will go through, right? So particles do not diffract. While a wave will just, when you get to there, it will just spread out, and then it still has the same set of particles. Does that make sense, everyone? So just understand what diffraction is about. Okay, so diffraction meaning if it's a wave, it will pass through a slit, but that slit has to be higher with the dimension approximately equal to the wavelength in the order of the wavelength. okay, while particles do not do that. So because they could spread out, a set of wave could spread out and start all over again and after the slit, that will create something called a diffraction pattern, meaning that if I have an obstacle, have two different slits, that means the wave come in, it will go form it will diffract in here and also in here. So if you have two sets of the wave, what happened? What we just talked earlier. You have two sets of wave, when they come in, if they come in phase, that will give you what? Constructive interference. But if they come in exactly out of the phase, out of step, they will be a destructive interference. So that means what? You're gonna end up with this dot and say you are using just a visible light, say, and I will see some you get this pattern. One area gonna be bright, and then you get a completely dark area, and you get bright and completely dark because you have that interfering, constructive interference, give you brighter intensity because the amplitude add up to each other. And then when they just happen to come in completely out of phase, what do you get? They cancel each other out completely, then you get the dark spot, the dark area, okay? So if you see this pattern, that will means what? They have interference and create they create this pattern. Yes?
The in-phase statement specifies that they have to be of equal magnitude. Does that equal magnitude only apply to double?
No, you could end up with different, this is a simple example. Say if they don't come in exactly the same altitude, say, then you end up with kind of a lot of noise. So it's not gonna be a good pattern. Yeah, they will still interfere in constructively and destructively. But the destructively is not going to completely cancel out because they're not completely aligned with each other. The frequency is not the same. Okay. Now, if the amplitude is not the same, they just add them up if they're in phase, but it's not going to be twice as much. I'm just using a kind of simple case. See how they interfere and how they reflect. Okay? Any question beyond that? So, and that's what we say so far. We said light could be described, wave could be described as in terms of wavelength and frequency, amplitude, and speed. Okay, so also we can see that it possesses these two properties. Okay, so we will have a set of wave, and we'll see these two properties. We will set my experiment. So, but then later on we find out that light also display particle property. Light is not only coming in as a set of wave, but also coming as their particles. How could that? It seems to me is contradiction, right? You say because a set of wave, like light wave, comes in, you could have diffraction, right? While a particle don't have diffraction. You know what I mean? So when I said earlier, I say particles do not diffract. But then I just telling you that light could diffract and could, seems like it should be able to diffract if you look at that as a particle. It turned out light actually, in the very beginning, I mentioned that earlier, light had dual properties. It could sometimes act in as a set of wave. It's wave light, sometimes it's what? Particle light. So it makes it very hard to understand, right? It's kind of, you say triangle is triangle, all of a sudden you say triangle is a circle. or it's almost like that. But it does light does behave like that. At certain circumstances, it behaves like a set of wave, which possess diffraction and interference. And then sometimes it actually acting like particles, bits, not continuous, but bits of light, things like that. Okay, the kind of depends which way that light is going to be, which way the light is going to behave will be depends on the circumstances, depends on the experiment you're setting up to run. Okay. So let's go, but all of a sudden we say, well, light also behave like particle. You get to prove it. You can just say, well, I think it's like particle. Somehow you get to prove it, right? And the next section will show you how we prove it. Okay. So let's go to the next section. So far, we're all talking about light as a set of wave. Now we talk about light as a display, particle properties. So that's what we say, limitation of wave model. Certain things you could use the wave nature to describe waves, and you could use using wave property, you could explain certain experiment. Okay. And now I want to show you that light also has particle nature. Okay. Which is through this experiment called photoelectric effect. So photoelectric effect showing light is also light consists of particles. Okay. So the photoelectric experiment is something like this. Say if I have a piece of metal, if I shine light to it, and we see something kind of strange. What happens is light coming in with certain kind of frequency. Okay, wavelength. So kind of depends on the frequency. I'll be able to see that electron could be, if it with certain wave frequency, electron could get ejected out, okay, with the correct kind of frequency, meaning the frequency had to be over certain value when the frequency of the light high enough frequency, well, then the electron could get ejected. So the electron, where the electron come from? The material. So it's the piece of metal. So metal consists of metal atoms. Each metal atom has electron on the outside. Inside it has nucleus. So the electron of, say, this piece of metal is an atom. The metal consists of atoms. So the electron from the atom going to get ejected. But only when what? When you have enough frequency. Okay, so it will be ejected. We could actually measure out its energy. The electron energy is the mineral electron. The ejected electron. not gonna go into exactly how we measure that, we just know that it could be measured. So, this is kind of not agree with what we expect. We expect that when you have light coming in, if I increase is, remember we said light energy is related to its frequency. Okay, so if I have light energy, let's write that down. We know that light energy is frequency, mu, and amplitude, which is your intensity. Which is related to the intensity of the light. So technically, I should be able to eject the electron with any kind of light. I just had to increase its intensity, right? Because we know that light energy is related to its frequency and its intensity. So if I shine light to it, I could be able to shine brighter light. Then I would be able to eject the electron. How come it's only limited to high frequency? Right. Yeah, higher frequency, higher energy. You can see that the electron will be ejected. But higher amplitude, the light be brighter, that means that its energy is also higher, should eventually eject the electron also. Does that make sense that way? But you can eject the electron if you don't have light that have higher frequency than certain minimum level, minimum value. Okay. Even though you increase the amplitude, increase the intensity. So for example, I shine red light to it, okay? I don't see anything come up, no electron coming up. When I shine blue light, the electron will come up because we already know blue light have high energy than red light, right? However, what if I using very intense red light also will provide me the energy you take to eject the electron, but it doesn't matter how bright the light is shining. As long as you're using red light, nothing can happen, okay? And that's what, yes.
So it's only depends on frequency, not energy?
Well, yeah, it's not just the energy. Even though frequency affect energy, right? But amplitude also affect energy, okay? But somehow amplitude does not affect it, but frequency affect it. Okay, so we had to explain that. Okay, so that's why I say what we expect is we say energy is related to amplitude, intensity or brightness of the light, and frequency nu, right? Also related to energy. Changing either these two should affect the number and the energy of the electron emitted. Should be able to vary or increase those two. That will give you the electron. But the second part does not. Okay, amplitude. Even I increase the brightness, I cannot eject that if I'm using certain frequency that is too low. Okay, so it's kind of inconsistent than what we think of. So and that's why I'm saying we expect that, but what we saw is this relationship hold true only if the frequency meets certain minimum frequency. Only the frequency go high enough, then the electron could get rejected. Yeah.
So if you meet that threshold of frequency, when you change the amplitude, does it increase the amount of electrons emitted then?
Yeah. yeah, you increase the amplitude, then you will, once you meet that minimum, the brightness will increase your number of electron voltage. Okay? Below this threshold, we call that threshold frequency. No electron will be emitted regardless